Okay, so we'll get started. Today's just going to be a blitz of various basic topics in group theory. Some of it will probably be a little bit new, or maybe how we say it will be new, but maybe most ideas won't be. The ideas themselves won't be new, just maybe a little bit about how we talk about them will be new. But let's start with something easy. So talk about subgroups. So G is a group, a subset, H inside of G is a subgroup. Well, it's almost too obvious to write down. If the identity element is contained in H, you can replace this axiom with just saying that H is not empty in the presence of the next two axioms. If X contained in H implies X inverse is contained in H, and X, Y, both in H implies X times Y. It's in H. You can cut that in. So if you look in like Dummett and Foote, for example, there's various lemmas. There are different ways you can cut down the number of things you have to check. But this is sort of the intuitive definition. I mean, it's just as a subset that's preserved under the extra structure you have. So it's a subset that's preserved under the multiplication operation and the inverse operation, and so it contains the identity element. And just like a vector, like a subspace, the vector space is just a subset that's preserved under the vector space operations. So, okay, so examples. All right. Maybe people could just start writing some examples on the board, and I'll copy them here, or you can say them out loud. Yeah, good. So 2 times Z times Z. So 2 times Z, it's one way you can denote the even integers. You can think of that as sort of, and the integers are also a ring. You can think of that as an ideal inside the ring. And in fact, that's sort of a good generalization. So let me write it down. If so R is a ring and I is an ideal, then I is a subgroup. Okay, great. What's another example? Yeah, good. So that's actually a special case. Yes, so if in this first case we did the zero ideal for a ring, the zero ideal is the additive identity, and that works for any group. So E, this is always a subgroup. It's a trivial subgroup. Okay, what else have we got? Yeah, so Antonio just wrote G contained in G. Well, the full subgroup is always a group. The full group is always a subgroup. So this is a trivial subgroup of a different variety. Great. If your group is just the trivial group itself, so the trivial group is the group with one element, which is just identity element, then these are the same. Otherwise, these are different. These are all, except for the even integers, these are all sort of abstract examples. Can someone give me like a more concrete example? Yeah, good. So we have like 2 by 2 orthogonal matrices inside of GL2 of R. In general, sort of you could do sort of any sort of matrix group inside GLN for any field, sort of where, yeah, so there's a nice, and by the way, there's a nice interpretation of like matrix groups. So like with orthogonal group, that sort of stabilizes the standard linear pairing. You have the sort of the standard symmetric inner product. That sort of makes sense. And that's it. It's particularly well behaved over the real numbers, but that makes sense sort of over any field. You can sort of write down that same bilinear pairing. More generally, you could sort of fix some other type of bilinear pairing, and you can sort of look at the group stabilizing that bilinear pairing. That would give you some other sort of subgroup. You could, so in particular, if you take sort of the standard alternating bilinear pairing, you get something called a symplectic group. So, and just for example, sort of shows up in physics and other places too, but okay. Shows up in math as well. Otherwise, I wouldn't know about it. I'm not a physicist. And anytime I say something like something shows up in physics, you should probably sort of take my knowledge. You should know that I don't really know any physics. So when I say something like that, sort of it's not such a precise statement in that. But okay, but in fact, this generalizes. I mean, so we saw like, for example, last time we sort of had SLN inside of GLN, so the special linear group. And that's just sort of the matrices with determinant 1. And SLN inside GLN, well, that's what we call it. We had sort of SLN, K, sort of inside GLN of K. And so sort of one concrete way you can find that is determinant 1. Or you could think of it as the stabilizer. So stabilizer just means thing that preserves of the standard multilinear form E1 wedge ENs of 3Ns. This is the sort of standard alternating. Wow, this is I was going to make, let me not write it down. What I was going to say was going to be a white lie, so let me just not lie. Or you could think of it sort of like the determinant. So the determinant is exactly sort of how this thing transforms. Another way to say that is like the determinant is a alternating sort of n linear form. And maybe this is how you saw determinant defined, it's sort of the unique up to scaling alternating n linear form. Okay. But anyway, this thing, and sort of in general, you can like, if you make any sort of construction using tensors, so bilinear forms, sort of this thing, sort of these are just examples of tensors, and so you can sort of make any construction using tensors, and then sort of so you can just like fix some collection of tensors, and you can ask like what is the group that fixes those tensors, that stabilizes all of those tensors, and that gives you some subgroup of GLN, and this is actually. And there's a precise sense in which every subgroup of GLN is given in that way, depending on how you interpret every subgroup. So if you work in the sort of theory of algebraic groups. So really like sort of if you give a rule that lets you sort of for every ring R, give a subgroup of GLN, then sort of that rule is sort of the group that fixes some collection of tensors. And this is well beyond the scope of this class, but sort of just to give you some perspective on life. Okay, anyway, good. So we have some more groups though, good. So R greater than 0 inside of R cross. Good, I like that one. Okay, maybe I'll throw one more out here, just sort of like we could have like D2N inside of O2N, or sorry, inside of O2. Right, and so when it's a subgroup, we use this less than equal notation instead of contained in notation. So this less than equal means a subgroup instead of a subset. So the dihedral group to an element, well, that's just sort of the rigid transformations of the plane that preserve the sort of regular 2n-gon centered at the origin, or the regular n-gon centered at the origin. And well, the first part of that sentence was saying it's a subgroup of O2. Like when you say these are the rigid transformations of the plane, well, that preserve the origin, like that is the group O2. That is the orthogonal group. So because this is sort of the thing that stabilizes the notion of distance. These are linear transformations that preserve distance. Because preserving this inner product is the same, like preserving the standard inner product is the same as preserving the standard notion of distance. Like you sort of define the notion of distance using that inner product. So at least definitely if you preserve the inner product, you preserve distance, and you can sort of actually check that it goes in the other direction as well for linear transformations. Okay, so I mean, oftentimes when we sort of define groups, the way we define them sort of is implicitly as subgroups of other things. Okay, good. So that's a nice set of examples. So let's move on from here. Let me do another example definition. So if G is a group and S in G is a subset, then I can consider, right, it's brackets S. So this is the subgroup generated by S. Okay. So this is example / definition. So, you know, I've told you what I want this to be. I told you sort of you fixing some subset of G. So like you're just some collection of elements in G. So you could have just like one element in S, or you could have like two elements in S, or you could have sort of an uncountable cardinal of elements in S, like whatever, it's some subset of all the elements in G. And so, I mean, this must be equal to the smallest subgroup of G containing S. Okay, and I want everyone to just think for, say, until like 2 minutes or a minute, somewhere between a minute and 2 minutes about why this makes sense. So when my clock hits 12:40, so a minute, you have a minute now. Think about why this sentence makes sense. Oh, minute's up. Okay. Someone explain it to me. If you're someone try to explain it to me. Maybe I should have been. Okay, good. So this is an excellent answer, and I want you all to dispel it from your heads. So this is an excellent and true answer, but it's sort of, it's the kind of answer, like, so, and this answer is sort of built on this, like, constructive, like this sort of constructivist instinct that we all have, where when you see a statement like this, what you want to do is build this, you want to build this subgroup. You want to build the smallest group, generative S, like the smallest subgroup containing S. And so you say, okay, what has to be in it? Well, like if I have two elements that, if I have sort of two elements, their product has to be in it. If I have three elements, their product has to be in it, and so on. And okay, I can sort of just take some all the things I can express as finite products, and like those all have to be in there, and then I just need to show that's a subgroup. So, and this is true, and like this can be made rigorous. It's a little bit, if you say it like that, it's sort of a little bit messy to make it really truly a rigorous statement, though. The idea, like the fact that this, I mean, you can do it, and it's maybe like a half a page, but like you, to sort of give a rigorous proof, this, like maybe you'd write down an induction statement to show sort of, I mean, I don't know, it's. Yes, so okay, so good. So this is slightly better. We'll come back to that point in a minute. Good, so this is a nice way to make it rigorous. Let me give you sort of a way to make it rigorous without sort of a way to describe this without introducing a new technology, or sort of having to make sense of sort of like these word problem issues or anything like this. You can just write sort of S is equal to the intersection of all subgroups containing S inside of G. So instead of trying to construct it from bottom up, you can just cut it down from the top down. So this is a non-empty intersection. So a non-empty, you're intersecting non-empty because well, sort of this thing contains S, but and in particular is a subgroup that contains S. So this intersection will contain S as long as it's not empty, and it'll be sort of non-empty as soon as there's one thing in it, because sort of all the things in it contain S. And well, okay, but G is in this because G contains S. So good. And then you just need to check sort of the simple statement that sort of the intersection of subgroups is a subgroup. But that's pretty simple. So let's leave it at that. Okay, great. So this is what I mean when I say the subgroup generated by S. And just for example, so if G is a group, so I guess if G is a group, then and G is an element, so I can just consider the subgroup generated by that element G, which would be sort of defined to be the subgroup generated just by the set consisting of that element G. Good. Well, okay. What's this group? So now you can go back to Michael's constructivist perspective. So someone's right on the board, great. Yeah, so this is just the set. So when you have one element, sort of it's not so bad to see that this is just a set of all G to the N for N containing Z. And so you can see this is, and the subgroup is actually going to be isomorphic to Z if G to the N is not E for any N. So if G is an infinite order, or sort of Z mod NZ if sort of for N, the smallest number such that smallest positive integer such that G to the N is equal to E. Okay, so this is all cases. Either there is some integer, in which case you take the smallest one and then you get Z mod NZ, or there's none and then you get Z. So this is and these are sort of cyclic groups. So, okay. So let me. Definition. So G is generated by S contained in G. So G is generated by some subset if just the subgroup generated by that set of elements is equal to G. Okay. So just as an example, well, I'll give you a non-trivial example, but maybe someone can give me a simple example first. Yeah, good. So I like these. You guys are very quick on your tautological examples. And by the way, you might have noticed already, I basically just switch colors at random when I'm writing. There's no rhyme or reason to it. I'm trying to develop a rhyme or reason, but it sort of doesn't exist yet. So the set of all elements in the group always generates G. Let me zoom out to see if other people are ready. Whoops. Oh, so someone at some point wrote you can use that the intersection of subgroups is a subgroup. People are like zoomed way out, which is why I didn't see that. But great. Whoever wrote that, excellent. Thank you. Oh, Antonio, do you have a question, or are you saying you wrote that? Yeah. Mm-hmm. It's also what? Oh no, I think if you zoom out, like we each have our own pan and zoom controls. So if you click on the top right, you can get a mini map. Like if you click the eyeball on the top right, you can get a mini map. You can sometimes see what's going on, although it doesn't always work very well. Yeah, so if you try and write close to where there's already other writing, then I'll probably see it. But it's maybe in, okay, well, yeah, for now we can just keep on going with this. Maybe I'll try and figure out a way to like stay at a, maybe next time we'll all stay at a fixed zoom or something so that there's more coherence. And then we can sort of switch pages every time I ask a question, and that will sort of maybe make it work better. So for now, actually, let's just switch. So I just added a new page that switch everyone to the second page. Okay, and now we're all at 100% and we're all looking at the same spot. So don't scroll and don't zoom. And if we fill up this page, then if we fill up this spot, then I'll just make a new page. Cool, thanks. Yeah, thank you. Okay, so right, so we have the subgroup generated by G is equal to G. Can someone give me a concrete example? Yeah. So NZ is equal to the subgroup generated by just this element N in here. And Z is also just, so in particular, Z is the group generated by 1. You also can do sort of the cyclic group Z mod NZ is generated by 1. Okay, and so good. So anyway, this is the example I wanted. Let me give you a non-trivial example. So PSL2 of Z. So this is equal to SL2 of Z mod plus or minus the identity matrix. So this is generated by, well, I don't want to write down the answers because I don't want to write down what it's generated by because so this on your homework to do this, but if you write down an element of order 3 and an element of order 2. So your homework is for SL2, but okay, you can get those for PSL2 pretty simply from the answer. So this is actually generated by an element of order 2 and an element of order 3. Okay, and we'll come back to that in a minute. We won't prove that, but I'll say something else about that. But this is pretty interesting because this is a pretty big group, a pretty big and like maybe not immediately obvious like how to make manipulations with it. So it might be a little bit surprising that it's actually generated by just 2 elements. Okay, there are many different ways one can think about why this is. Good. So a group. So continuing sort of my definition is cyclic if it is generated by a single element. And we just explained above, sort of, that's either, and it's one of these examples that we just gave, sort of a cyclic group, sort of the same logic up here is just either Z or Z mod NZ. So in which case, your group is isomorphic to the groups Z or Z mod NZ. Okay, so a group is finitely generated if it is generated by a finite subset. So for example, this PSL2 of Z is generated by a set of 2 elements, so it's a finitely generated group. But of course, and this should be, so let me say, yeah, I'll come back. I was about to make some sort of some philosophical remarks, but let me sort of let's do a few more examples first. So give me another example. Give me some more examples of finitely generated groups. So that's good. So any finite group. Let's just write on the board. So e.g. symmetric group on n elements. Yeah, great. So any finite group is, well, we already saw any group is generated by the whole group itself. And that's a finite set if you're a finite group, so good. Good. Okay, and well, that basically covers the examples I wanted to. From time to time, my dog scratches at the door and decides she wants to be in here, and then sort of at some point she'll decide she wants to leave, and I'll go let her out. But anyway, good. So any finite group. So what's a example of a group that is not finitely generated? Great. So the rational numbers with the addition. So I think Sandra just wrote that on the board with a question mark. So can someone else besides Sandra give a quick explanation for sort of why this is not finitely generated? Okay, actually, so maybe let's take till like 4 minutes and everyone can think about this. So till 1 p.m. So try and think about why this group is not finitely generated. So a clean argument. Okay. Does anyone have what they think is a particularly clean way to say it? Okay. 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 Yeah, good. So let's say it this way. Yeah, so good. So we can basically something I was saying, if we have a generating set, a finite generating set, it looks like this. we take the product of the denominators, and then, well, the subgroup generated by S is just the intersection of all subgroups which contain S. And what you're saying is that this is contained in the subgroup generated by 1 over D, where you take D as the product of the denominators. And well, that's definitely not all of Q, because 1 over D plus 1 is not in it. Great. Yeah, that's a nice way to say it. Okay, good. And so, I mean, Q with addition is still a interesting group to consider. I mean, and it's like, so, and the real numbers are also not finally generated as another example. So infinite generation doesn't play quite the same role in group theory that it plays like in ring theory and module theory, for example. So like in module theory and ring theory, like notions of finitely generated are sort of extremely important. Like, so when you're doing algebraic geometry, like, and I think you guys did sort of basic algebraic geometry last term, like, and so that's like the Null-Stellensatz is a statement about sort of finitely generated rings over a field, like finitely generated algebras over a field. So these finite generations hypotheses come up quite a bit. In group theory, maybe not as much, at least depending sort of the variety of group theory you're doing. I mean, a lot of group theory, like, and especially a lot of this class, is just about finite groups, and then sort of you're automatically finitely generated. But then once you leave finite groups, sort of there are, like when you leave finite groups, like the most natural things to consider are like things like, I don't know, like the real numbers or like GLN of R, like things like this, which are not finitely generated groups, but sort of satisfy, like we're not finitely generated, but sort of satisfy other nice properties. So it's useful to have this notion around, but it doesn't play sort of quite the same central role it plays in ring theory. So there's a notable exception to this, which is so abelian groups. So in the theory of abelian groups, well, so a group is abelian if so the multiplication is commutative. So if AB is equal to BA for all A, B, and G, that's the definition. And okay, well, and these are particularly nice, and you already studied them a bunch last term, because what's another name for an abelian group? Yeah, great. So someone just wrote Z module. So an abelian group is just a module over the ring Z. What is a nice algebraic property of the ring Z? Yeah, okay, so some people, at least someone on the board knows where I'm going. So Z is a principal ideal domain. And so finitely generated as a group, as an abelian group. So finitely generated as a group for an abelian group. Well, that's the same as sort of finitely generated as a Z module. I mean, essentially, by definition, the Z module generated by some like a set of elements is just the smallest Z module containing them. Just like it's the same definition for a group, and since Z modules and groups are the same thing, these notions are the same. And so, what's the big theorem about finitely generated modules over principal ideal domains? Yeah, good. So Sandra says classification. Can someone tell me the classification theorem in this case? Okay, great. So it's almost written on the board. So someone wrote it on the board, but left out one part. So the classification in this case is the statement that so any finally generated abelian group G isomorphic to I'm going to use slightly different notation. Why in a second. To z to the n for some n plus z mod m1z, z mod m2z, and so on all the way up through z mod mkz. So for m1 divides m2, and m1 could be equal to 2, m2, and so on, all the way up to mk. And so for a unique choice. So any group sort of is isomorphic to a group of this form. So any finally generated abelian group is isomorphic to a group of this form. And so this is literally just the statement of the classification theorem for finally generated modules over a PID expressed for Z modules, which are abelian groups. If you don't remember that classification theorem, like that's the most important thing. Like that's one of the most important things that was covered last semester. Presumably it was covered last semester. Is that, yeah. So if there's one thing you should sort of take away from graduate abstract algebra, it's that theorem and like how to deduce like Jordan normal form and rational normal form from it. So that's, but anyway. Right, so okay, so and then somehow like finally generated Z modules sort of, we talk about them all the time and they come up all the time. So this is sort of, and they have this nice structure so where you can really sort of pin down what the structure of them is. So this is an important class for finite generation, like is something we really do care about. Just a word about this classification theorem. So the uniqueness, so G is isomorphic to such a group, and sort of the choice of n and the choice of sort of m1 through mk, these are all sort of uniquely determined. But there are many automorphisms of this group. So there's not a unique isomorphism. There's not a unique way to sort of choose an isomorphism between G and this group. There just is an isomorphism for some choices, for some sort of unique choice. But the isomorphism itself is not unique. This is something that you don't spend a lot of time thinking or worrying about as an undergraduate, that you sort of eventually as a grad, well, not maybe as an undergraduate, maybe, but like in sort of a lot of standard undergraduate classes, about this distinction about sort of when two things are isomorphic and when they're canonically isomorphic. But like this is probably one of the most important distinctions to sort of make in your head as you're learning more advanced mathematics, is sort of which isomorphisms are just up. There is an isomorphism, but you had to make some arbitrary choice, and which isomorphisms are canonical. And so a canonical isomorphism is much more powerful than a sort of up to a choice isomorphism. Okay, that's sort of philosophical side note. This is the point here: is this isomorphism is not canonical. Okay, so good. Let me make. Well, actually, let's take a 5-minute break, and then I'll sort of come back and sort of explain the notation. So if you look at what got written on the board, instead of this sort of this plus sign, like this circle plus sign, which is like \O sum in tech, or it's called a direct sum, the product sign was written on the board. And so in this case, these are equivalent, but in general, they mean two different things. And sort of the right thing to mean here is actually this one. But we'll come back to that. Yeah, so let's start again at 1:16, I guess. No, I forgot to hit record. Thank you, Thomas. Thomas pointed out I forgot to hit record after the break. So if you're watching the recording of this, you skipped like 15 minutes. Sorry about that. You can look at the notes. Okay. So as I was saying, this like categorical notion, so in terms of like this universal property of maps out of it, if you do sort of that universal property in sets, you get disjoint union. If you do it as abelian groups, you get this direct sum. And if you do it in groups, you get something else, which is called a free product. You should denote this with a star. Okay. And so I don't really want to prove this exists. So you can give an explicit construct, like, so the free product is sort of defined to be, it's defined to be a group that satisfies sort of this mapping property. And so that's how you should define it. So sort of you define it in terms of its universal property. You should say it's any group satisfying this mapping property. And then, and universal properties always pin things down up to unique isomorphism. So just like sort of the tensor products pin down up to unique isomorphism by its universal property. So these things are all pinned up to unique isomorphism by the universal property. But then you still have to show at some point that there is some construction that works to know that such a thing exists. So as soon as you have a construction, you can forget about it because you can just sort of, the main thing you want to use is always the universal property. And like when you're writing a proof, when you're making an argument, you want to use the universal property. But you do, and to show it exists, at some point you have to give some construction that works. And so this is the construction is sort of via sort of all possible words. So a word is just sort of, you write down sort of a formal product of elements in sort of these different groups, a finite formal product of elements of these different groups, and then you sort of give some rules for, then you have to give some rules to say sort of when two words define the same element, and you have to prove that sort of defines a group. This is sort of a delicate procedure, and this is not the only way to do it. So there are nicer ways to do this that we won't talk about in class. Let me say, so another way and a better way is via sort of algebraic topology. So you can use sort of the Van Kampen theorem. But I don't want to, I don't want to go into that. And this is sort of something you should think though in your head, like the nicest construction of sort of free groups and free products is sort of using algebraic topology, sort of the place where they arise sort of somehow the most just sort of spontaneously on their own. Okay, good. So, and this comes back to sort of the Michael's constructive definition of the subgroup generated by a set of elements. So if I is a set, then sort of the free group f of I is just the free product over all I and I of sort of the group generated by a single element. And sort of it's characterized by the property that sort of a group homomorphism from f of I, this free group, to another group G is just the same as a sort of map of sets from I, so let's say it this way. To set sort of underlying G. So this is just unwinding the definition, like unwinding the universal property of free product. And so giving a map from Z to a group is just sort of giving an element in that group. And then sort of you're doing that, you're giving an element to the group for every sort of index in your index set I. So, and let me point out, this sort of relation has a name. This is, F is sort of left adjoint functor. I don't want to get into that if that's not language you know, but if you sort of know something about adjoint functors, then this is sort of a useful thing to remember. Free constructions are always sort of adjoint functors to forgetful functors. And if you don't know it, you can either forget, I just said, if you don't have any idea what I'm talking about, you can either just forget that sentence, or you can sort of look it up and sort of, you might sort of be conceptually enlightened at some point for having done so. But this is a side note, like this isn't going to play an important role in anything we do. Okay, and so, good, so this is, right, so in particular, if G is a group, and if S contains G is just a set of elements, sort of, well, we get a map from sort of the free group on S to G, and just sending sort of the index S to the element S. And sort of the image of this map is equal to the subgroup generated by S. So this is exactly sort of what Michael said when I sort of pushed for a justification of this sort of constructivist notion of sort of the group generated by a set of elements, is that you should sort of take the free group and take the corresponding map from a free group to G. And that's true. So this is almost a tautology that this is true, and you can check it as an exercise if you'd like, sort of to write down like a 2-sentence proof that this is true. Okay, but so this is sort of one way you can sort of make, and this is sort of how you can go back to this perspective that to get this sort of group generated by the subgroup generated by a set of elements, they can sort of just take all the products of those elements. But this gives sort of a nice way to do it. In particular, well, so if G is a group, then and sort of S contained G is a set of generators for the group. Then you can present your group as sort of the free group on S. So this notation for surjection onto G. So you get a surjective map from the free group. You take the kernel of this. So let me call this surjection pi. So you get G is equal to the free group on S modulo the kernel of pi. So I guess this is something I didn't define, but I'm assuming you know and remember. So there's another important type of subgroup called a normal subgroup. And normal subgroups are exactly the kernels of maps. So you can sort of, there's a different sort of internal way to think of them. Sort of they're subgroups where if you conjugate by any other element, you stay in the subgroup. But like the right way to think of them is normal subgroups are kernels of maps of groups. Okay, well, anyway, so, and then sort of anytime you have a normal subgroup, you can sort of form the quotient group, it's just an abstract group. And so this sort of isomorphism is called the first isomorphism theorem. So in general, sort of if you have a map of groups, you get this sort of, the domain modulo the kernel is isomorphic to the image. Here, the image is all of G. So we get this. Now, kernel of pi is itself a group. So I can sort of pick, so if I fix generators P, then I get sort of a surjection sort of from f of P onto the kernel of pi. And so I can sort of write G is equal to sort of f of S modulo sort of the image of f of P. So this free group. So I'm writing sort of G is a quotient of a free group, and then sort of, well, its kernel is another group, so I can write that as a quotient of a free group. And well, why am I doing this? I want to point out that this is what it means to give a presentation of a group. So this is the same as presenting a group. So like we have sort of this D4 is equal to the group generated by RS modulo the relations R to the 4 is equal to 1, S squared is equal to 1, and RS R is equal to S inverse. And so what that is really saying is, that's saying these two elements, so this is supposed to be D8, the dihedral group on 8 elements. So what this is saying is this dihedral group on 8 elements is generated by these two elements R and S. So we have a surjection from the free group on sort of 2 elements. So and then we have the kernel of this. Living inside. And the kernel of that map, so I never said this aloud. Again, a kernel is just sort of all of the elements that get mapped from my homomorphism to the identity. I guess this is something I'm assuming that you already know, but if this isn't something you know, then you should take very seriously the recommended reading on this weekly handout, and sort of go back and review the definition, like the basic definitions of group theory. So the kernel of pi goes in there, and then sort of, so this was just using the first part. So like this, having the surjection is just the content of saying that D8 is generated by these two elements. And then the second part is telling you generators for the kernel, this map. So the second part is telling you that you get a map from sort of Z star Z star Z going to here. So these relations are sort of 3 things that have to be 0. So another way to say this last one is RS is equal to 1. Good. And so, so this sort of goes to R to the 4. This goes to S squared. This one goes to sort of RS. That's where sort of 1 in each of these factors is going. So, and this is not something we're going to use abundantly, but somehow it's useful to know what you're actually saying when you say you have a presentation of a group. So this is what you're saying when you have a presentation of a group. You're saying you have sort of some elements that generate the group, and you have take the corresponding surjection from a free group, and then you have the kernel of that. And now you have some elements which generate the kernel of that surjection. So that's literally, like when you give a group presentation, that's literally what you're saying. That's sort of how you make sense of it. And this was essentially, yeah, so I should stop because it's 1:46, but this was essentially a tour of like the internal constructions you can sort of naturally make in group theory, and sort of how they compare with like notation you may have seen before and sort of ideas you may have seen before. Sort of if this is all new to you, like if free groups are new to you and sort of you're not used to thinking about universal properties and categorical language, sort of this is fine. none of this is specifically things we're actually going to use so much, but it is sort of helpful to sort of just, and maybe the thing I want to drive home is that like for this lecture is when you're thinking about like internal constructions in the category, like in particular in the category of groups, like you want to think of them in terms of like universal properties and maps. Like this is sort of a nice way to think about them. And especially when you're writing proofs sort of that use these constructions, like you should never write a proof that involves a direct sum where you're using the explicit construction of a direct sum. Like you should write the proof using the universal property. Just like for tensor products, like you never write a proof using tensor products where you use the explicit, well, okay, and people do, you shouldn't ever write a proof with a tensor product where your proof like uses an explicit construction of the tensor product. Like your proof of the tensor product should only depend on the universal property. Like that's why you have a universal property. You have a universal property so you can make arguments sort of correctly without depending on a construction. So maybe, and this is something to take away from this lecture. But okay, so after this Warp Speed tour, like next week, we're going to sort of start doing things we're actually interested in understanding. Okay, well, I'll stop there. So I'll stop the recording and